the other option is if you stay in this room, we'll do kind of a deep dive into linearization, and I'll share kind of how I teach linearization for my freshmen, and there'll be time for questions, and we can spend some time on this. Obviously, linearization is a very challenging topic, and so we hope that this will help sort of make sense of it for you, and also maybe give you some ideas about how you could share this with students. Okay, so let me make a whiteboard on my iPad. So as we go through this, please just stop me and shout out questions. I know it took me a long time to wrap my head around linearization, so it's definitely a tough topic. And I want to answer your questions. If I'm going too fast, please let me know. So I always like to start off by thinking about a really, really simple example. And it might seem like almost trivially simple, like it's so silly, it's almost like silly. But if you understand how it works in the simple example, you can also kind of see how it works with more complicated numbers. So I like to think about sort of just a made up data set. Let's say we invest different amounts of money in the stock market or something. And then we look at how does that affect our return. And let's say we just invest some really simple small numbers, $1, $2, etc. And then we look at what kind of return we get for each of these. Obviously, this is kind of silly made up data. And so if we graph this relationship, I'm sure that everyone can predict the shape of this graph ahead of time, but obviously we get something sort of like this. So we have some nonlinear data, and then obviously our goal here is to try to see if we can figure out which variables are proportional to which ones, or what's actually linear to what. In order to do that and to understand what we're doing, and not just like memorize, like, oh, if you see this shape, then you should do this linearization. There's two questions that I think we should ask ourselves that are really, really important questions. So let me, I guess I'll just put this at the bottom of the screen. Okay, so the two questions that I think we should think about are, the first question, I sometimes think about it like, what's the most basic relationship? Or basically just as X is getting bigger, what happens to Y? If we don't know that, then we don't really understand what's going on. So please feel free to shout it out. In this case, as the investment gets bigger, what happens to the return?
Becomes squared.
Yeah, and I guess with this question, I'm trying to like split things into parts, if that makes sense. So like, I don't really care. I mean, maybe it's squared, maybe it's not. I think it's hard for us to just eyeball it and see that. All I want to know is just like, as the investment gets bigger, does the return like get bigger, or does it get smaller, or does it stay the same? Like, just like a really, really simple thing. At least for now. Go ahead, Vincent.
It gets bigger?
Yep, and I know that that's kind of obvious, right? But I'm trying to like go really slowly and in small steps to make it really simple. So what we've got right now is, as the investment gets bigger, so does the return. And that's a good thing, because if you remember, our goal is we're going to try to get something that is linear and that has a positive slope. So as the X gets bigger, so does the Y. So you might ask, like, why are we asking that question? One of the linearizations I think will be useful if as one gets bigger, the other does not get bigger. So, okay, so we know like as X gets bigger, Y gets bigger. I'm just going to like draw two little arrows. So I know like as my one variable is getting bigger, so is my second one. And then the second question is, how does it change? So we know as X gets bigger, the y is getting bigger, but there's lots of ways that that could change. So it could be like for a constant increase in x, the y also increases constantly. If that was the case, it would be linear. But it could also be like for a constant increase in x, the y increases by bigger and bigger amounts, or maybe for a constant increase in x, the y increases in smaller and smaller amounts. So this sort of how question, which is the second one, is a little trickier question to answer. And there's a couple tools that we can use that will kind of help us to decide this if it's not obvious. And for some of you, I'm sure it's very easy and obvious, but let's say we have a student that is not sure how the return is increasing for a constant increase in investment. So the first tool is the tangent tool. I'm sure that you guys all remember tangents in your math class. So obviously the tangent is the point on the graph that touches it but doesn't cross the line, and it tells us about the slope. And the slope is useful because basically that's what we're trying to get after in question 2, is like what's happening to the slope. So my challenge for you guys, and I know this is silly, but I actually do this when I teach it with my students. So I just draw some like random little curve. Can you guys annotate the screen? So you can feel free to just pick a dot on my curve, and please draw the tangent on your dot, and hopefully we can get everyone to do at least one. Great. So someone drew a tangent. Thanks, Vincent. And while we're doing that, what questions are there so far? Am I going too fast?
Hey, Scott, I'll ask a question.
Mm-hmm.
Are you doing this at the freshman level when you're talking about this?
Yeah, we do for our honor students. We don't require it for our regular students. I think they could do it, but it just would involve maybe like the cost benefit is not maybe worth it. It would involve a lot of effort and a lot of time to get them to really understand this. But for our honor students, we do it, and I think it's definitely worth the investment.
And do your honor students, have they had geometry at this point or not yet?
Most of them are either in geometry or have had geometry.
Okay, so they're familiar with the idea of tangent at that point.
Yeah, most of them are, but not all of them, which is part of why I do this activity. So if they, at least from my experience, if I draw the curve and they practice drawing a couple of these, or they see how it works, even if they've never heard of tangent before, they get it. Like, okay, there's only, these are the only lines that touch the curve and don't cross it or whatever. So I do explicitly talk about this in case there's someone who hasn't seen it before, but most of them have.
Yeah, I've done this with 9th grade students who are just in Algebra 1, and as long as they've seen the concept of slope, they can usually get an idea of a line that touches the graph at one point, for example.
Yeah, okay. Totally. Good questions. So now we know how to draw tangents. So if we look at some of the tangents on this graph, obviously they're getting steeper. So that tells us something about how the return changes when you increase the investment by a constant amount. There's 2 other ways that you can look at this. These other 2 ways are maybe not quite as good as the tangent method, but they're nice to just like kind of check your work or just other ways to think about it. So the first one, I just like call these rise over run triangles. If we think about a linear graph, so like let's say we think about the diameter and circumference graph that we did yesterday in the circle lab, we all know that slope is like rise and run. So I usually draw the run part first and the rise part second. So we could increase the diameter by any amount, but like obviously we're trying to keep things simple. So like, what do you guys think? What is the simplest number of all numbers?
1.
Exactly, 1. So we're going to increase the diameter by 1. And every time you do that, the circumference always goes up by the same amount. And obviously that's because for a constant increase in diameter, you also have a constant increase in circumference. So let's take a look at what would sort of a similar thing look like on our curved graph. So if we increase the investment by $1, you can see there's an increase in return. And if we do that for a larger investment, there's still an increase in return, but it's a much bigger increase in return. The one thing I will caution you with these sort of rise over run triangles is you've got to keep the run constant at 1. If you start changing the run and you make it different, then it's not meaningful anymore because you're changing two things at once. So you got to keep the change in X always just be 1 because we'll keep that simple. And then we look at what happens in the change in Y. Well, for a constant extra dollar of investment, there's relatively small change in return, and now there's a bigger change in return. Any questions about the rise over run triangles? And then
I go back just a second and ask a
Sure.
quick question. How do you introduce this to at the freshman level to tell them why it's important to linearize the data? I
yeah.
can do it for AP, but I can't see how I'm going to.
Yeah, that's a good question. So obviously before we get into linearization, we've done some of the linear graphs. So like we've done the knot lab, we did the circle lab, and we've written equations, right? And at that point we've like used the equations to like make predictions about maybe, you know, something that it would be hard to see on a graph because you're going off to 1 million or something.
Okay.
And so they get that it's useful to be able to write an algebraic version of the relationship. And we obviously cannot simply do that from a curve. So you can see like, okay, so we're trying to make it linear so that we can get that equation. And I think it's a good justification of like why it's useful.
Thank you. That's a big help.
Yeah, good question. Okay, so there's one other thing that we can look at to just like understand how these things are related. And this one too, you've got to be careful that you sort of don't misuse this. But if we look at the actual data, the numbers, so if you look at the investments, and you can see the investments going up by 1 each time, a constant amount. And if you look at the corresponding return, you can see it's also going up, but it's not a constant amount. The return is growing by larger and larger amounts, even though the investment is just growing by a constant equal amount. So all these things are saying, whether you look at the numbers or the tangents or the rise over run triangles, they're all saying that for a constant increase in investment, for each additional dollar of investment, the return gets bigger by larger and larger amounts. So now we've like answered this like question 2. Any questions? Okay, great. So let's think about a couple mathematical tools that we can sort of employ. So one tool we can employ is something squared. Another tool we could employ is the reciprocal. And let's just like take a quick look at like what happens when you employ these things. So I'm just going to use a really simple number set. Let's use 2. Let's do 2, 3, 4. So let's say this is my data set 2, 3, 4. And then if we square it, obviously we get 4, 9, 16. So you can see for a data set that was increasing by a constant amount, the square of that data set still increases, but no longer by a constant amount, now by a larger and larger amount. Does that make sense? And then if we look at the reciprocal, so this is obviously 0.5, 0.33, 0.25. So if we look at our original data set that was increasing by a constant amount, now we've got something that is decreasing. It's not really constant anymore, but the important thing is that we turned a data set that from increasing to decreasing if you do the reciprocal. I also want to point out that there's nothing special about these transformations. If we wanted to, we could try to linearize with like an x cubed or natural logs or all kinds of stuff. But fortunately, in like simple, like, you know, physics pretty much through AP Physics, we just don't need those. We're not going to see those relationships. So like, we don't need to learn those, even though like theoretically you could linearize with all kinds of mathematical transformations. Does that make sense? Or you could try to linearize with lots of math transformations. So we've got these now we could square either axis, and we could do a reciprocal of either one. It doesn't really matter which one you flip. If you think about like as one variable goes up and the other goes up, if you flip one of them, they'll be opposite, or if they started opposite and you flip one of them, they'll be the same regardless of which one you flip. So like to me, this reciprocal is like a flipper function. It turns things that were increasing into things that were decreasing. And then the square function is something that like changes by how much the thing is changing for each interval. So if we go back to our original graph here of an investment versus return, do you guys see why the reciprocal one is not helpful? We already had, as the investment went up, so did the return. We don't want to flip it. That's not helpful, right? So if we're trying to like see what could be linearized, or what could we do to try to linearize this, we're going to square something. And to know which one we want to square, that's where we look at, you know, the tangents or the rise over run triangles. So can anyone explain, what do you think we should square here to try to linearize this? And why do you think that?
We square x?
Sure. And do you want to like explain what's your reasoning, or like the why?
Because if we want, in order for a linear relationship to exist, if I increase something, one side by one amount, the other side should reflect that multiplied by a coefficient, should be some sort of constant increase every time. And to do that, if we square the x, we'll be able to achieve that relationship, sort of constant ratio between the x and the y.
Yeah, we already have the y's growing by more and more every time. So if we want something to be proportional to that, well, we're going to need that thing to grow by more and more as well, right? Which it wasn't initially. So let's try to do investment squared. I'm kind of running out of space here, so I'm going to abbreviate investment to just I. So I squared. And again, I know that these are very trivial numbers, but okay, so I squared is this. And if we plot this data, we have like, so if I do my investment squared versus return, I can do, I have like 1, 1, 4, 4, 9, 9, 16, 16, and like 25, 25. And you can see now we've got a line. And I think it's important to point out here that the reason we got a line is because like this one and this one squared were inherently proportional before we even did this. I didn't make it linear. It's just, that's what the number set were. We just like found something that was already there. We discovered something that was already true that we just didn't know for sure. So we have this graph here. And we kind of talked about this last class briefly, but a really important question is, do these two graphs, do they convey the same information or different information, and how come either way? Like fundamentally, do they tell the same relationship, or is it the same data, or is it different?
Same relationship.
Sure. And like, could you, like, how do we know that? Like, how do you justify that?
Because even though each graph shows a different representation of the data, in the first graph, you just have investment dollars versus return dollars. The second graph is still showing the relationship between the two data. It's just showing investment dollars squared versus return dollars.
Yeah, sure. So like, just to kind of play devil's advocate, and I think it's worthwhile to do this, because when I first saw these two graphs, I said, you know, hey, wait a second, this is not the same information or relationship being showed. We've got a curve here and we've got a line here. That's a big difference. Also, we're squaring, and this is investment squared versus this one is just investment. So we're plotting different variables on the two graphs. So on the surface, it looks very different, but I will argue it's actually the same. And it's because those two changes kind of cancel out. So like one way to think about it is to make these two graphs, I fundamentally was using this same data to make this one and also to make this one, because all I did was just square this. So it's still based on these numbers. Obviously, if these numbers changed, these would change too. And additionally, another way to think about this is, let's say we thought about sort of an algebraic equivalent of this. So let's say I wrote an equation like this. Saad, let me answer your devil's advocate in just 1 second. So let's say we look at these three different equations. On the surface, they look very, very different, right? They're equal to different constants. I'm raising x to different powers. I don't want to worry about negatives. But do you agree fundamentally they're all conveying the same thing? They're all x is the same value in all of them, even though they look quite different, right? Mm-hmm. But it's really the same thing, just like these graphs are sharing the same data or displaying the same data or same relationship, but just in different ways. And sorry, let me look at the, okay, what if a student asks if we can take the square root of y? That would also, oh yeah, great question. And the answer is that would work, right? So there's nothing wrong with that. If you had taken the square root of return, you would also get a linear relationship. And it's the same exact graph as this one, right? And so there's nothing wrong with that. The only reason I choose to do this is just because it's simpler. I think that squaring things is simpler than square rooting things. And then we'd have units of like square root of dollars. I mean, I know that the units get weird and no matter what we do, because what's a dollar squared? But I just choose to do it this way. If the student wants to do it that way, it's perfectly fine. There's nothing inherently wrong with that. Good question. Other questions so far? Good question.
Another question for this. So how do I, like when we're looking at it in the linearized function, how do I convey what x means in words? Like in this particular case, what does investment mean? Investment squared in words. How do I tell them what that means now?
Yeah, a good question. And I mean, really, the answer is it doesn't mean anything. In investment squared, I don't know what that means, right? Like the investment times the investment, it's the thing times itself. It doesn't really have a physical meaning. So that might be an argument to say, and I think it's a good question, well, like, why are we messing with this graph if it's graphing something that doesn't really have a physical meaning, right? And that's a good question. But I would say that this graph has one big advantage. It also has one disadvantage. So the disadvantage is what you said, that investment squared, we're not really sure what that is. It's just some mathematical abstraction. But the advantage is that it's linear, right? So this graph here has the advantage of just being simple things that are plotted, and we know what those variables are. We can imagine them. We know what it represents easily. But it has a disadvantage of being a curve. This graph has the advantage of being linear, so we can see what things are proportional to what, which allows us to write an equation. But the disadvantage of we're plotting some weird abstraction that it's hard to know. We don't know what investment squared is. And let's see, Vincent says, can we say it's a mathematical construct? Yeah, for sure. I totally agree. Vincent, does that make sense? Saad, good question. So basically, they both have advantages, but then obviously the nice thing about this, which is why we went after this whole thing, is now we can write an equation and we can say like, okay, well, return equals whatever the slope was times investment squared. Yep, plus the intercept, whatever that is. Maybe it's 0, maybe it's not. So now we've linearized this, and we can write an equation which is useful to describe this relationship that was curved. Is the idea fit to curve? Yes, Ty, good question. Yes. So notice that we can do this without the computer, and now we're not just pulling equations out of yeah, you can do it with a computer or not. So let's think about a couple other examples.
I have a quick question.
Sure, go ahead.
So you say like it was originally proportional, but that's because your data is specifically like exact. Like, but with experiments and stuff, you have error. So it's, even though it looks like, you know, a straight line fits it, it's not going to actually be proportional.
Yeah, you're right. So the it's never going to be a perfect line on the linearized version. But I would argue that, like, if let's say it turns out that investment squared is fundamentally, or it should be, proportional to return, after you do the linearization, this line will be a better best fit line than it would be here if you tried to just say, well, maybe this is linear. Does that make sense? Even if it's not perfect because of error, it's still going to be better. So that actually brings up a good point, which is after we do a linearization, so like on the worksheet, it says like we're making a guess or we're doing a test, because we don't know for sure until we graph the mathematical transformation. We don't actually know that it's going to be proportional or linear, right? And I think that one thing that's tricky, and it's worth sharing this with students, is when we draw curves in, like, on the board or on a whiteboard or whatever, we oftentimes draw it like this in order to be clear, and there's nothing wrong with that, but it's not really what happens with real data, at least in physics. So what happens with real data in physics is much more often something like this. And you're wondering, well, is that a line or is that a curve? I don't know. It's hard. You can't just eyeball it, right? So it's not usually as extreme of a curve as this one. So this one is really clear. So how do we tell what's a line and what's a curve? And also, how do we tell, was our linearization successful? Did it actually make things more proportional or not? There's two ways that you can tell. So let's think about the really extreme case. So let's say that we thought that this graph was linear. Obviously it isn't, but it shows how this rule works nicely. So if you try to put a linear fit on something that is clearly curved, you notice that almost all the data points on the ends are on one side of the best fit line, and all the data points in the middle are on the opposite side. That is telling you that this is a bad best fit line. That's not what you want to see. So if the data really was linear in the first place, what we would want to see is just random above and below, no specific pattern, no systematic data points above and below the best fit line. And in my opinion, this is the best way to tell if something surely is linear or not. So like if we look at this data here, and I'm not drawing this perfect, but to me, this looks like a curve. It's not a very steep curve, but you can see in the middle, the data points tend to be on the top, and on the ends, they tend to be on the bottom. That's not a promising sign for truly linear data. And so after we linearize this, if we saw randomly distributed points about the best fit line, I would say that the linearized version of it is more proportional. The second thing that you can look at, although I always caution students with this because they inevitably use this the wrong way, but the second thing you can look at is the correlation coefficient. So when you put the best fit line on, Logger Pro or whatever graphing software you're using will give you some correlation, some number, like maybe it'll say like 0.987 or something. And so it's basically a measure of how perfectly linear the data is. So if you had a correlation of 1, that would be a perfect line. If every single data point was exactly on the line, and positive correlations are for slopes going up, negative is going down. Let's not worry about negative slopes right now. So the reason that students get into trouble with this is they look at this correlation and they say, wow, that's pretty high, 0.987, it's pretty linear. So I guess the data is linear and we're done. but they are forgetting the fact that the correlation ranges between 0 to 1, and 0 represents just complete randomness, dots all over the place. That would be correlation 0. So even if you have a curve, if you have slightly curved data, it is going to look a lot more like a line than it is random data. So you cannot ever just look at the one correlation and say, oh, it's a high correlation, I guess we're done. What you want to do is do your linear transformation, so do your linearization. So let's say we think like on this one, maybe we should square b. And then we take a new correlation. And let's say we get like 0.9. So that is telling us that this linearization improved the proportionality. So basically now we know, like, okay, this one, b squared is more proportional to a than b was to a. And so basically we were probably effective in the linearization that we attempted. What questions are there on how to tell if you successfully linearized or not?
So with the R squared value, are you just having your students look for a higher value?
Right. It's just the comparison that matters. That's it.
Mm-hmm. Okay.
Good question. Okay, so let's try a couple more examples, and then potentially, if we have time, you can try to do some of your own linearizations. So let's say we did one that's like a graph like this. Let's say study time versus score on a test. That's not perfect, but let's say I plot some data and then I put a best fit line. We get something like this. You can, I guess, one or two other notes is the bigger the range between the smallest and the biggest value of the data point, it makes it easier to tell if the data is curved or linear. For example, let's say we had something that was obviously a curve, but we only took data right here. So basically that's forcing us to zoom into this little part of the graph. Do you see how that part of the graph would look linear even though it's not? So the more spread out the data is, the more able we are to tell if the graph is truly linear or not. So I like to ask students to try to get a 1:40 ratio between the smallest and largest independent that they choose when they set their values, if they can. It's not always possible, but if they can, that's a nice thing to have. Okay, so let me throw up those two questions that I think are important. So for this one, does anyone want to shout out, what do we think is the answer to the first question? Just the most basic relationship, the simplest thing we can say about how study time and score are related?
Same as before, the more you study, the higher the score.
Good. So right off the bat, that rules out the inverse function. Do you guys see why that's not going to be helpful here? And then what about the answer to the second question? So for a constant, for each extra hour you study, we already know the score is going up, but by how much? Like for 1 hour compared to the next hour?
Has diminished returns.
Yep. And so that gives us a clue of like, what could we try to linearize this? So this one, yeah, it looks to me, and we're not even sure of this until we do the linearization, but it looks to me like the data is kind of a side opening parabola, because again, we have that like systematic points in the middle are above and points in the end are opposite of that, which is saying it's probably not a good best fit line. It also just makes sense, right? Like if you, the first hour you study has a bigger impact on your score than the 100th hour, because at that point you already kind of know everything, and maybe it helps a little bit, but it doesn't make a big difference.
What do you do if the data is like ax plus b squared or something?
Oh, good question. I don't think that we can linearize that, although I'm not sure. I do know that for any lab that I can think of that we've done in like physics or even probably AP physics, like I don't think that the relationships are really that complicated. So I don't know that it comes up, but there are certainly some relationships that you wouldn't be able to just linearize. Good question. Okay, so let's think about another sort of graph. And this skill isn't directly related to linearization, but it's the same ideas, and it's really helpful when we get to like curves on a position versus time graph. So let's say we looked at a graph of like how quickly or how smartphones were adopted over time. So let's say we are graphing, I'm going to call it percent adoption. And I'm going to just say that percent adoption is the ratio of smartphones over total phones. And so let's look at like how might percent adoption change over time. Okay, so I'm just drawing those little hashes to like separate this graph into kind of 3 regions. Let's call it A, B, C. So does anyone know, let's suppose that this was the true data. I'm not sure that it is, but in which region were the most new people adopting smartphones per year, and how come?
B, because the slope is the greatest.
Do you guys see why? So a lot of times students will say A, and the problem is that although the number of smartphone adoption like per year is increasing, it's still getting steeper all the way up to the end of this. And then this slope here at the beginning of this region is the same very steep slope that we saw at the end of the curved part. And like, so what's happening to the change in the percent adoption every year in part C, and how does that make sense?
It's decreasing because most people have smartphones at that point.
Right, so there's just not that much more opportunity to switch to smartphones because everyone already has it, or almost everyone has it already. So obviously there's kind of a limit because it's a percent. We can't go over 100%. We can think about what the slope on the graph means. Obviously, this graph should never have a negative. Well, I guess if people went back to flip phones, it could have a negative slope, but that seems unlikely. We could think about what the intercept means. Like that's when, you know, when in 1992 the smartphone was invented and no one had smartphones. And then we could also think about like how we'd want to linearize this. So although as we talked about before, we'd kind of have to do something different for this part of the graph compared to this part of the graph. Any questions? Okay, so let me share maybe one more example. I know this is a lot of talking. I don't usually like to like just talk this much. This is maybe the one topic I do that more than anything else for in my physics class. So here's some real data. This one is a kind of a chemistry experiment where you look at how volume and pressure are related. So you could imagine we have like a canister of gas or something, and there's like a piston in there, and so you can move the piston around that changes the volume that the gas is in, and then obviously there'll be some effect on the pressure. So we have this data here. Can anyone answer those 2 questions that I always think are a good starting point for linearization? What's the most basic relationship, and then how are the things changing?
As the volume increases, the pressure decreases.
Good. And so right there, and it's for this relationship that I mostly ask question number 1. Like that's a clue about what mathematical transformation we could try. Does anyone know what might be a good thing to try to linearize this one?
Inverse.
Right. So just to kind of be careful, let's put a best fit line on the original data. And I mean, it's pretty easy to oddball this one. It doesn't look linear, but you can see that we've got a systematic above and below pattern, which doesn't look good. We've got a correlation of, so negative just because it's going down. So let's not worry about the positive or negative, but the initial correlation was 0.84. Let's try a linearization. And so obviously here the numbers are starting to get a little messier. And again, even if the numbers were even more messy than this, but they fundamentally follow this relationship, it doesn't matter because we're doing the same thing. So instead of us manually doing the calculation of 1 over the volume, also, this is kind of building on a question that Saad mentioned. It doesn't matter if we invert the x or the y. Do you guys see why? Because either way, they're now, as one increases, so will the other one. However, when we write the equation, it's a little nicer to say like y equals m times 1 over x than it is to say 1 over y is equal to x. So I always encourage my students to invert the x, even though it doesn't matter. Okay, so let's try to do a new calculated column. And so we can call this 1 over volume, and it has units 1 over meters cubed. So you want to remember to do whatever you did to the variable, you also do to the units. And so then we can do an expression, and logger pro makes it pretty easy. It's nice to just find the variable. Okay, and so now we have this new calculated column. All it did was just 1 over the volume variables. And then let's try to make a new graph here. And logger pro usually does some silly things to start. So let's make the graph that I wanted, which is this one. And then if we put a new, I mean, partly you can just eyeball this because it's kind of silly, really obvious data, but you can see that this one is way linear. We have a much higher correlation. So it's very clear that the linearization was successful, that 1 over the volume really is proportional to the pressure. Okay, so I also want to think about, and depending on the linearization you're doing or the data set, this doesn't always work, or sometimes this you might sort of think about it and then kind of reach a dead end or something that doesn't make a whole lot of sense. But I like to think about like slopes and vertical intercepts on both the pre-linearized graph and the linear one, if I can. I think it's useful to and we kind of did this yesterday, but it's useful to go back to think about like vertical intercepts and slopes on both graphs if you can. So I'm sure you guys would agree that by definition, the vertical intercept has to be on that y-axis, right? And the interesting thing about all the points on the y-axis is that the x is 0, right? So sometimes my students don't always see this, but I just graph a bunch of points and point out that what the points have in common is the x value is obviously 0 for any point on that red dotted line. Of course, we're not studying x, we're studying volume. So when we want to think about the intercept, we're basically saying if the volume is 0, and this one is, you can see there isn't really an intercept. It would go up to infinity, right? So if the volume is 0, then pressure is infinite. And like, can someone explain, like physically that makes total sense for this experiment. Remember, it's a gas chamber and there's a piston and there's gas moving around. How does that make sense?
It only adds so much pressure before the chamber explodes.
Yeah, I mean, if you have no volume, you've smashed it so there's no space for that gas. Of course, the pressure goes through the roof, right? That makes intuitive sense. We can also think about the x-intercept. So eventually, like theoretically, this thing might have an intercept on the x-axis. So in that case, we'd be talking about infinite volume, because we're like gone all the way over on the x-axis, and then of course there'd be 0 pressure. That also makes sense. How would that, like, how can we physically make sense of that?
The particles never touch each other.
Yep. It's like a gas tank the size of the universe, right? So there's no pressure. Okay, so that makes sense. So now let's think about the intercept on the linearized graph. Once again, we're talking about when x is 0, except that x in this case is 1 over volume. And we've got a little bit of a problem there. Can someone describe what the problem is?
The volume would have to be infinite in order to get 0.
Right. So we really can't make 1 over something be 0, right? So let's at least try to get close to that. So let's just say 1 over volume is at least close to 0, even though we can't get to 0. Let's just get close as we can. And so we're talking about really big numbers. So I always ask my students, like, what kind of volumes would make 1 over volume be close to 0? And sometimes they say things like, 0.1, and then it's like, I'll ask them, like, throw it on the calculator and see what that is. That's not very close to 0. So eventually they realize, like, okay, we need really, really big volumes for 1 over volume to be 0. So basically, we're saying when 1 over volume equals 0, and that happens when the volume is really big. So we're also saying when the volume is infinite. Is anyone confused how these two statements are essentially the same thing? Okay, and so then if we just interpret the graph, so when the volume is infinite, the pressure is 0. You can see on the y-axis the height is 0. So that makes perfect sense. We just have the x-intercept on the previous graph is the y-intercept on the linearized graph. So once again, even though on the surface these graphs look very different and have different shapes, they all convey the same information. And so the linearized one could be useful to write the equation.
How would you talk about the units of the slope of the linearized graph?
Sure. So yeah, I do like to point that out because students definitely have trouble with that. So so if we start with, obviously slope is rise over run. So we've got pascals and then divided by 1 over meters cubed. So we got this like nasty double fraction that we would like to simplify. So I always remind students that it's really important to think about, like, where's the major fraction? Like, is it the top one or top bar or the bottom one? And it's the top bar in this case because we're doing, like, obviously slope is rise over run or pressure over whatever x is. So this one is the big fraction, and then the minor one is the 1 over meters cubed. So we like to simplify that. So let's just use the fact that anything over itself is 1. So let's multiply on the bottom meters cubed over 1, and that will get rid of that nasty double improper fraction, whatever. And of course, in order to not change the overall quantity, we need to do to the top the same we do as on the bottom, so that this is just a 1 in disguise. So then the meters cubed on the bottom cancels out, and then the meters cubed is on the top. So our units would be like, if we wrote an equation for this, it would be like pressure is equal to our slope. So we've got 3.4, and then that's Pascal meter cubed times 1 over volume plus our intercept, which a lot of times we kind of already said theoretically that the intercept ought to be 0 here, and it's already pretty close to 0. So I think that's a good reason to just say plus 0 or not to put an intercept. So we have these weird units. One thing that I like to show students is for any equation, whether it's like a simple kinematics equation or some complex linearization like this one, the units should at least make sense, even if we're not really sure what is a Pascal times cubic meter. So I like to do a unit equation. So to do a unit equation, you just throw in the units for each variable. So like pressure will be pascals. In the unit equation, I don't care about values. I just care about units. So, okay, pascals equals 3.4 is a number. I'm going to forget about it. We've got pascals times meters cubed in the slope. So I'll write that because those are the units of the slope. And then 1 over volume. So that's 1 over meters cubed because that's the unit of volume. And then plus 0, let's forget about that. And so you can see that the meter cubed on the top and the meter cubed goes away. And so basically we're saying pascals equals pascals, and that's at least a sensible statement. So the units do like they make sense, even though I don't know exactly what a Pascal times meter cubed is. I don't think we can, at least I don't know how to visualize that. Good question.
So basically, you're just looking for kind of dimensional consistency in
Right.
the units.
Mhm.
And you're okay. All right. Sounds good.
Good question.